Good afternoon. I hope you enjoyed the day so far. We are here to talk to you about cybersecurity and operational technology world. My name is Stephen Seiden. I'm president of Acquired Data Solutions. Acquired Data Solutions is a 23-year-old small business specializing in test and automation, test and evaluation, test and measurement, and system integration in the OT space. As you can see in our medallion, we cover a lot of the different interfaces from RF to vision and motion and video and optics. And you can see how those apply to all the different industries that we have in this medallion. So today we're really talking about engineering and vision in the cyber age because all these products need cybersecurity. And we are focusing today with my two colleagues to talk about this subject. With me today is Leighton Johnson, who was going to talk about the risk management framework, and Tony Barber, who's going to talk about the analysis that you have in these old OT systems that we are going to go through this afternoon.
Good afternoon. I'm Leighton Johnson. I'm the Senior Cybersecurity Engineer for ADS. I have over 40 years experience in computer security, operation activities, test and evaluation mechanisms, and in cybersecurity.
Hello, I'm Dr. Tony Barber. I'm a system engineering executive. I'm also supporting ADS as a program manager. I have over 20 years of experience in system engineering, cybersecurity, and IT.
So today we're going to go over how the DoD initiatives align with the risk management framework in this artifacts. We're going to talk about organizing the cybersecurity activities that you'll need to do within your division or company. We're going to talk about creating a cybersecurity plan for operational technology. We're going to discuss what the cybersecurity posture is and how to evaluate that for operational technology systems. And we're going to talk about how to prioritize and down select security controls for implementation. So, what is operational technology? Obviously, as test and evaluation professionals, we're out there every day looking at systems that are both hardware and software dedicated to physical processes through monitoring and control of physical systems. And so that includes anything manufacturing, test automation equipment, power control systems, utility companies, chemical filtration systems. And what's interesting is, as recent as July of 2020, NSA and the CSIA organization, CSIA is the new Cybersecurity Infrastructure Security Administration, have just recently put out a article talking about there's a lot more cyber actors out there trying to get in critical infrastructure through exploiting internet accessibilities through operational technology assets. So that's really what we're talking about, is how to limit that exploitation and lock down the system.
So, back about 10 years ago, NIST, the National Institutes of Standard and Technology for the US government, produced a mechanism by which government systems will be evaluated around their security efforts and activities. They've produced this document known as the Risk Management Framework mechanism. And what they did is they started with looking at all the possible areas that IT would need their mechanisms around risk and understanding what the risks are. And they would do this through a process initiated based upon the business models that the government had put together back in the 1990s around categorization of the information systems based upon the information types that were involved. Those mechanisms will be in the low or moderate or high arenas around the data and understanding what controls needed to be put in to handle their confidentiality, integrity, and availability. This resulted in them producing a mechanism by which they created a baseline of these states of understanding within the organizational system that was to be looked at. And as a result of that, we would conduct an assessment of the vulnerabilities, the threats, the impacts in those arenas around low, moderate, and high. And this would then result in us being able to create a security baseline that was prioritized based upon those risks. The areas of coverage that these controls would include areas such as accessing the system, making sure that we recorded the mechanisms, making sure that the equipment was in its inventory, it was identified, how it was handled, how we got onto those systems, how we did our interchanges through identification, how things were handled when things went wrong as part of those processes, how we would fix them, what was going on on the interfaces and internal to the systems as they were connected and working. As part of this, they also ensured that each organization would then develop a method called a system security plan that would show what was connected, where it was, how we assessed the risk, how was it acquired, what were the activities that were done during the entire system development lifecycle of that particular activity, and how therefore it was protected in both the confidentiality and the integrity, and as well in the availability arenas.
So we talked a little about IT and the various NIST policies and procedures used to protect information technology. But as we shift over to operational technology, we want to give an example and a walkthrough of how we went through a typical test equipment cybersecurity assessment. And that include the categorization, the boundary selection, the interface identification, the software and hardware inventory, and the control baseline. So on the first step, which is your security categorization, also coined as your FIPS 199, this is where we do an assessment of the confidentiality, the integrity, and the availability of the system. So in this process, we look at the information types and we determine basically the categorization, whether it's a low, moderate, or high, for the NIST assessment for the applicability. The second step here is the system model and authorization boundary. This is an exercise done within the SSP. This is where we evaluate the test equipment or the actual operational technology, and we determine what the authorization boundary is that we're going to assess. So, what is inside and what is outside? As you note, on the left hand side, we have our internal infrastructure. So this is outside of the assessment, but this includes things like the operator, the network, and any of the power distribution that goes to the actual instrument. On the right hand side, we have the unit of the test. So, what is the test equipment testing? And as you can see in the operational environment, we're looking at things like tanks, planes, missiles, and so on, because this is done from a defense standpoint. Number three here, also within the SSP, are the various interfaces. And so, one thing you want to look at is our assessment on operational technology is focused on not only the components, but the interfaces and the software drivers. And so, here we have the internal interfaces. This is all the things that are happening inside of the authorization boundary. We have the external interfaces, which is the communication outside of the boundary. And so that also includes your local area network, and as mentioned before, the unit under test. Fourth, here we have within our SSP, it's the software and hardware, which includes the drivers, the operating systems, the browsers, the system managers, and so on. These are very important. So not only are we looking at how we are acquiring the particular components and whether the components have vulnerabilities, we're also looking at the communication paths or interfaces between each component, but also the drivers and the software that's loaded on those components that could have its own vulnerabilities that we should be assessing. Next, we're looking at the control baseline. This is where we evaluate the current state of what's going on within the cyber area for this particular instrument, but we're also using this as a way of understanding applicability for the base controls and enhancements. As you can tell, if we do a full assessment, this could take a lot of time and could require a lot of resources if we do this manually. So one of the first steps we do is we do a down select, or we identify applicability as it applies to that particular instrument. And that includes evaluating whether or not it is something that the customer may implement versus the manufacturer, whether it's already been implemented in the space, if it's partially implemented, or if it's not implemented at all. So in this context, the next area that we're walking into is the risk analysis, which is really part of the risk modeling area for operational technology. The first thing we have to identify is how will we do an overall assessment? Is this something we will do manually, or will we use some form of automated technology to actually do the assessment? So some of the requirements we are looking at is the evidence-based model-driven assessment. We're also looking at the component assessment adaptable to OT. Since we do have operational technology overlay, we want to make sure that the risk analysis toolage can leverage and do an assessment on operational technology. We're looking at an extensive cybersecurity knowledge base. We're looking at the ability to prioritize controls, so understanding which controls are most impactful to mitigating the actual security posture. And finally, we're looking at something that's going to provide a quick but comprehensive assessment. So, looking at the risk model, one of the inputs to this, or at least multiple inputs to this risk model, includes the system description, the data types, the data sensitivity, the information exchanges, and the data flows. Within the Blade Risk Management tool, which is the tool we're going to leverage to do the risk modeling in, the two inputs that we have here is an architecture model or a word template. Within the tool, there are various features that we should be looking at to actually do the assessment, identify and calculate the risk, and actually list out the vulnerabilities as they apply to each risk. On the left-hand side, we have the analysis tool that actually focuses on the list of risks, the risk cube, and the count distribution. On the right-hand side, we're looking at the vulnerabilities per risk. Keep in mind that each risk has a number of vulnerabilities associated with it, and it ties the risk approach to the actual cybersecurity approach as well. Next, we're also looking within the tool, the list of attacks per the risk. And so this model actually provides us an overview of all the various types of attacks that could occur. And we're looking at the attack patterns or the attack graph. So understanding exactly how an attacker can, in multiple ways, exploit a particular vulnerability. All right, now we're at the outputs. The first output list we have here, we have the top 10, although there are plenty others, are the performers. And when we say performers, we mean the various assets or components that apply to building out this technology. Right now, we have Visa as the top performer, so that's the riskiest performer that we have here. There could be multiple reasons why this is the riskiest, but the actual tool we're doing in automation gives us some insight so that we can focus in on 1 through 10 in that order to determine how to perform some level of mitigation. We're also looking at the vulnerabilities by risk. Keep in mind that the vulnerabilities are areas where attackers can exploit. And so part of this effort is the combination between vulnerabilities, risk, attacks, and attackers. From an output standpoint, a context of how we need to do some analysis to understand exactly what mechanisms, what controls we need to put in place in order to protect that particular performer or asset or component. We're also reviewing the attacks. This is another output. So this is giving you the attacks as it applies to the risk. The risk we have here in this example is the corruption of block data. As you can see, we have the performer or the component at the beginning of the statement. We have what happens or the actual exploit that could occur. And then we have who it could occur by. So we have the hacker here, we have the OT supplier, and so on. Next, we have the top 10 attackers. And although there could be many more, what we have and we have identified is that right now we have a listing of attackers that you would normally think about when you are trying to figure out the appropriate attack pattern and who the actual malicious actors are. So on the left-hand side, we have supply chain as sort of the top one, which is the malicious supplier. In the middle, we have so the internals. We categorize that the internals as the malicious maintenance personnel, the malicious operator, careless operator, clueless operator, and software failures. And then we have the external, which is sort of like the nation state, the hackers, or any other targeted or non-targeted viruses that could impact that particular instrument. And final output here is the risk cubes. I should be very familiar with most of the risk management practitioners out here. This is where the 58 risks that was in our example are outlined and graphed. Two things to keep in mind. First is the actual risk cube. It is based on the organization. So the risk appetite will change how the coloring happens across the actual risk cube. And then last is the fact that in order to reduce the actual risk, you would see a reduction in the likelihood because you cannot reduce the impact. And so the likelihood of a risk occurring would, in most cases, when you actually do a mechanism or implement a control, will reduce to improbable.
Thank you both, Leighton and Tony. To summarize, we just wanted to have this slide about the business values and how we saw increased productivity because we got to focus on the analysis and insight rather than the investigation and research. We really were able to optimize our approach because we were able to augment models quickly and recalculate risk rather than having to do anything by hand. And we were able to get comprehensive results because we had an expanded knowledge base that we were able to address automatically through automation. So what that really did was give us a great return on investment where it decreased our costs, our number of man hours, and really increased robustness of our system. And really the main benefit to the customer was it was able to reduce the number of man hours and people by really about a fourth or a fifth of that, 2,000 hours to 390 man hours. So thank you, and we are now open for questions and answers.